Okay, so we are back with our next example. The question states, find the acceleration due to Earth's gravity at the distance of the moon. Okay, so as we know, our acceleration due to gravity on the surface of Earth is 9.8 meters per second squared. Okay, so this is on the surface of Earth. Okay, so we want to know then the acceleration due to gravity at the distance of the moon. Okay, so we will use this equation here, okay, that we solved for in lecture as well. So the acceleration due to gravity is going to be equal to g, which is our gravitational constant, times our mass, which is, in this case, it's going to be the mass of the Earth, okay, divided by our radius squared. Okay, so our distance from here to the moon is going to be 3.84 times 10 to the 8th meters, okay? And our mass of the Earth here is going to be 5.8 times 10 to the 24th kilograms. Okay, so what we'll do is we'll plug these numbers in, sort of like they did here. I can pull that gravitational constant from right here, 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared, times my mass, which is 5.98 times 10 to the 24 kilograms, divided by my radius, 3.84 times 10 to the 8th meters squared. Okay, so we can plug that into a calculator. 6.67, negative 1, oops. And I get 2.7 times 10 to the negative 3 meters per second squared. Okay, so what this tells us is the acceleration due to gravity that the moon feels is much smaller, okay, and that it's feeling Earth's gravity, okay? So it's Earth's gravity when we're that far away, okay? So that's not the moon's gravity, right? This is the gravity of Earth if we are at this distance, okay? We're not on the surface of the Earth. We are 3.84 times 10 to the 8th meters away from the Earth's surface. Okay, so that was part A. Part B states, calculate the centripetal acceleration needed to keep the moon in its orbit, assuming a circular orbit around Earth, and compare it with the value of acceleration due to Earth's gravity that you just found. Okay. So with this one, I'm going to need to go back here. And it's centripetal acceleration. Okay. So centripetal acceleration. I don't know the tangential velocity, but I can figure out my rotational velocity. Okay. So I'm going to go ahead and do that. That's an R, sorry. Ooh, that's bad. There we go. All right, so my omega, if we go back, we can calculate it as delta theta over delta t, okay? And if we're looking at one orbit, that is going to be 2 pi radians, right? And we're going to divide that by our time. So how long does it take for the moon to go all the way around, or one orbit around Earth? That is going to be 27.3 days. So 27.3 days. Okay, so we'll have to convert that into seconds. Okay, so I can go ahead and show you. Actually, instead of doing it right there, let me just go ahead and write that on a separate line. It'll make it easier to read. So delta T is that 27.3 days. Okay. So first we need to go from days to hours. So in one day, there are 24 hours approximately. Okay. In 1 hour, there are 60 minutes. Okay. In 1 minute, there are 60 seconds. Okay, so now we're at seconds. So take that, 27.3 times 24 times 60 times 60, and that gives us 2.36 times 10 to the 6th seconds. Okay, so 2.36 times 10 to the 6th seconds. Now I can determine my omega. So I'll say 2 pi divided by that number I just found, and we get 2.66 times 10 to the negative 6 radians per second. Okay, so that's my omega. Now I can calculate my centripetal acceleration. I plug in my R, which is 3.84. 3.84 times 10 to the 8th, I think it said. Yes, perfect. Multiply that by my 2.66 times 10 to the negative 6 radians per second squared. So I'll take this and square it, and then multiply it by 3.84 times 10 to the 8th. And I end up with my acceleration of 2.72 times 10 to the negative 3 meters per second squared. Okay. So that's my centripetal acceleration. Now I want to compare it to the value that we just got, which you can already see that it's very close. Okay, and so we can divide the two. We can say AC over G, 2.72 times 10 to the negative 3. I'm ignoring the units because they're the same. Divided by 2.7 times negative 3. And I get about 1.0 approximately. Okay, so these two are pretty much the same value. Okay, so my centripetal acceleration, in order to keep the moon in orbit, okay, and my acceleration due to Earth's gravity at the distance of the moon, they're about the same. So that means we're going to keep the moon going around us, right? We have that right, the correct acceleration, and then therefore the right forces involved to keep the moon in orbit around Earth. Okay. Okay, so moving to the next one. Not sure if you guys can see that, but it's glitching out again. Super fun. Okay, so this next example states, given that the moon orbits around Earth orbits Earth every 27.3 days, and that it is an average distance of 3.84 times 10 to the 8th meters from the center of Earth. Calculate the period of an artificial satellite orbiting at an average altitude of 1,500 kilometers above Earth's surface. And I put a note here that this is about the radius of Earth. Okay, so for this question, I am going to use Kepler's law now. Okay, so Kepler's third law, because I'm comparing two things, okay, and I am looking for period given a different period of a different planet or orbit, satellite, another satellite, okay? So let's see, we have T1 squared over T2 squared equals R1 cubed over R2 cubed, okay? So this is the equation that we are going to use, okay? Okay, so I'm gonna go ahead and label some stuff. I'm gonna say that my first period is given to me, and that is 27.3 days, okay? And it doesn't tell me to convert it to seconds or anything. I can kind of tell that because this is, these are just ratios, so I don't really need to convert. But for just the sake of it, I am going to go ahead and convert it into hours since I am looking at a satellite, an artificial satellite that's orbiting us. And I just know from experience that they, don't take days to travel around the Earth. They more than likely take hours to travel around the Earth. So I'm just gonna go ahead and convert this into hours real quick, okay? Oh, what am I doing? 24 hours is one day. Okay, so I'm gonna go ahead and do that. So 27.3 times 24, that gives me 655.2 hours, okay? And that's my first period here, okay? And so I am wanting to solve for that other period. Okay, so just reminding myself, sorry. Okay, and so now I'm looking at, it's given me an average distance. So R1 is 3.84 times 10 to the 8th meters. Okay, and the average altitude, which is almost its distance, right? Because remember when we're looking at a radius, okay, we want to look at from center to mass to center of mass, okay, this distance. So if I'm looking at the Earth and the moon, okay, my radius is from that center to that center. That is R, okay? So what I'm looking at here is, whoops, if my satellite is here, this is my little satellite, okay? I'm looking, it tells me my altitude here, which is just the altitude above Earth. Let me go ahead and make it a different color. Okay, that's my altitude. But I need to include the radius of Earth. Okay, I'm gonna have to add that on. So R2 is not just going to be my altitude, it's gonna also be the radius of Earth. So I'll have to add that. Okay. And note that this is in kilometers, so I will also need to do a conversion. So 1,500 plus 6,380 gives me 788. And I need that in meters. So I will have to say how many meters are in 1 kilometer. That's 1,000. Okay, so I multiply by 1,000 and I get 7.88 times 10 to the 5th meters. Okay, so that is my second radius. All right, so now I can use this equation here to determine that second period value. Okay, so I'm going to go ahead and scroll a little bit, and I'm going to take that equation and do a bit of algebra. And I'm going to say T2 squared is going to be equal to T1 squared times R2 cubed over R1 cubed. Okay? And to solve for it, I will need to square root both sides so that T2 equals T1 R2 cubed over R1 cubed square rooted. Okay? So I can plug these values in. Let me go ahead and do that. So I have, oh, my dog's whining. She's like, Mom, aren't you done doing physics? Never done. Okay, so there's my first period. And then I have my R2, which is 7.88 times 10 to the 5th meters cubed, divided by R1, which is 3.84 times 10 to the 8th meters cubed, and that is in a square root. So we get, I'm going to go ahead and break it down into a couple steps here. 7.88 times 10 to the 5th cubed divided by 3.84 times 10 to the 8th cubed, square root of that number. So this is 9.3 approximately times 10 to the negative 5. Does that seem right? I think so. Okay. Now we multiply that by 655.2 hours, and I get 0.0609 hours. Let's go ahead and convert that to minutes and see if that's right. 1 hour, 60 minutes, 60 minutes. That does not seem right. Okay, well, I found my minor mistake here. I just forgot one little thing here. This should have been a 6, not a 5. I misread it on my calculator. So that takes this off. Whoops. So it's to the 6th. Okay. And so this value was wrong. So let me go ahead and fix that. Sorry, my dog is whining. Okay. So we've got that value divided by 4 to the third square rooted. Okay. So I've got 2.94 times 10 to the negative 3. Okay, then I multiply that by 655.2, and I get 1.93 hours. Okay. So little glitch, and that does kind of teach all of us, especially me, to be careful when you're going through your calculator, because sometimes you kind of go too fast, like I probably was, and I didn't put the right value here, and I put a 5 instead of a 6. Oops. Okay, but that drastically changes your answer. So be careful when you're doing that. Make sure it makes sense. So as you could see, when I got through that and stopped, I was like, wait a minute, that doesn't seem right. Because there's no way when I calculated it that they could travel all the way around, a satellite could travel all the way around Earth in like 3 minutes. I was like, that doesn't make sense. So always make sure to kind of validate your answers and make sure that they make sense. Because if they don't make sense, they're probably, not right. Okay. So just like that, be careful, just like I need to be. Okay. Anyway, so that is the end of my lecture here. I will be putting up all of your labs and a little bit of information about the lab tomorrow, and kind of wait for that. As far as homework goes, I have your homework that's going to be put up, and I will hopefully begin grading your tests a little later this week, so watch for that as well. Okay? All right, I will see you next time.